what I had last time, maybe with slightly different, flavor or emphasis. But, so I'm not gonna draw the picture of Newton having an apple fall on his head, right? But the idea was that, so Newton gravity, we'll just call it this time. And the idea was that the terrestrial, say, projectile motion and the motion of the moon around the Earth are governed by the same law. So, same law, and that, you know, that's why we can refer to the apple and the moon. Apple and moon. And then you can kind of go through it. You say, for projectile motion, here on Earth, so what do you have there? You know, you launch something, right, that's flying through the air, and I didn't say this last time, but you can relate that to the lunar orbit in the following sense. You've got mg is the weight, right? And what do you have for this path here? You've got mv squared over r for the local, where r is the local curvature of the trajectory. And then you can also say F is equal to mg, and so I'll just say local curvature. And then if you're looking at the moon, and you're looking at it in the same way, you know, something orbiting a central body, then you've got, if it's a circular orbit, right, the local curvature is r, the distance from the central body, you've got that circular orbit there. And as far as the force goes, it's going to call this M1 and M2. So by the general Newton's law, you've got the force that you're looking for is going to be proportional to M1. And by Newton's third law, equal and opposite, you're going to say that the force must also be proportional to M2 by Newton's third law of motion. So having looked at it in that way, then you go to that final argument I talked about. You're looking at a orbit, and you're now saying, yeah, the force is equal to mv squared over r. Right? And the v squared over r is actually purely a kinematic expression for the centripetal acceleration. So here's where this argument comes in. You've got 1 over r, you've got m over r. The v is for a uniform circular motion, 2 pi r over the period, and that's squared. Okay. And so you've got an m and a 4 pi squared there. What you've got is r squared over r t squared. And this last step is where Kepler's third law comes in, because the t squared is going to be proportional to r cubed. So I'll just put the proportionality there. So you've got r squared, r cubed. So t squared proportional r cubed for a circular orbit. And that turns into 1 proportionality sign equals 1 over r squared. So sometimes people want to just teach Newton's law without knowing about Kepler's law, but I think it's when you have a chance to know how the argument was made, then definitely a good thing to learn. You may make some great discoveries someday too, and so it's good to see this. Anyway, that's how the 1 over r squared law is inferred, and then he proved it by instead of, this was, Kepler's laws was for the planets, okay? Then he verified it for the Earth and the Moon. That's what I gave you guys last time to plug the numbers in and see if it works out. And it'll be close enough, you'll be pleasantly surprised, okay? So verified it on the Moon, for the Moon, and the next step is to just be really bold and declare it to be a universal law. Okay, so it's a few steps. By the way, Kepler's laws were completely empirically discovered by him. He evaluated data, and he fit the data, and he found out. So when Kepler found this law, the whole conceptual framework of Newtonian mechanics had not yet been invented. Okay? But yeah, this was Kepler's third law. Kepler's third law. And then you get the 1 over r squared. So now I'll just kind of continue along the lines of what we had last time. So a little more explanation. So the next step would be universal gravitation. And that's the hypothesis that centuries of testing pretty much showed, but it wasn't immediately accepted. So the next step is universal gravitation, and that means any two masses are going to attract like this. So any two point masses, M2 separated by separation R, are going to have that force between them. And the force, of course, manifests itself as an acceleration between those masses. But we'll just write the force is going to be proportional to the product of the two masses divided by their separation distance squared. And if you release them from rest, that implies an acceleration towards each other. That's the idea. So you have that for any two masses. And these are point masses. That's worth mentioning. What about extended bodies? Well, an extended body will be an integral over point masses, and we'll do that later, either this semester or next semester. Where you start with point masses, and then if you have an extended mass, you do an integration over all those masses. And Newton was able to do that too. And that's why he was able to prove. Story is he didn't publish until he could do the proof, but he assumed for a long time that a spherically symmetric mass would attract just like a point mass. And then eventually he proved it with integration. And Sam was pointing out that you can prove it pretty quickly with Gauss's integral theorem if you have that at your disposal. Because it's the kind of thing you've seen in electricity and magnetism too. That's usually where you've seen the proof. But so that was the next step, to declare it universal. And of course the next step, and you guys can look up Cavendish, then Cavendish actually tested this in the lab, so to speak. He made that balance that thing I showed you last time, right? And when Cavendish finds G, and I think it's 6.61 times 10 to the minus 11 Newton meter squared per kilogram squared. Look that up and make sure I got it right. But having found that, then we finally have F equals G. I'm going to do it this way, NM over radius of Earth squared. You have that point mass property too by then. And if you call that your weight on the scale, bathroom scale, so to speak, then you would see that you've got the unknown for the mass of Earth and the mass of any central body. Solve for I think Cavendish said that he has now weighed the Earth, right? He's been able to determine the mass of the Earth, but only when he actually found out what the gravitational constant is. Good. So that's the progression of ideas. And finally, I think I mentioned this too, you can look at the other heavenly bodies, say Jupiter, and if you can resolve the size and period of the orbits of the moons around Jupiter, then you can really make the same argument, because you get the local, I'll just write now, other planets and their moons. So with other planets and their moons, you've got the, say, Jupiter here. Jupiter is orbited by a whole collection of moons. And first of all, Kepler's third law is verified for the whole collection of moons. But of course, there's a different constant there. And if you know this, then you can get the mass of Jupiter by the period and size of the orbits. Okay? So that can be calculated off of that. Yeah, so actually now let's set this up. So generally you've got a central body, and for now we've got circular orbits, right? We're gonna go into the other orbits later. But circular orbits and a central body over here, generally circular orbits around a central body. And you can always set these things up the same way. So you'll just set up Newton's law now. You'll say I've got G, the central body's mass, and the orbiting satellite. So there's your force law, right? Now that we have all these things. And that is mv squared over r. Okay. These cancel. And the mass, we can just write r v squared over g, or r 2 pi r over t squared g. I'm just going to write et cetera, because at that point you're just invoking Kepler's third law. Okay? So Kepler's third law is a real tool of the astronomers now. So what would we have? We'd have 4 pi squared r cubed over t squared. Okay? And when you recognize here, of course, this ratio is your Kepler's third law, and this is how it's related to the mass of the central body. So this side of the equation, you're analyzing orbits. Okay. This r is, say, the distance from the center of the central body to one of those orbiting planets. Okay. And there's your mass of that central body. And what happens is that for every little moon orbiting this planet, you're always going, right, this is just the mass doesn't change, so it's always going to fulfill that Kepler's third law. And that was discovered already in Newton's time, so he was using the data for Jupiter to make his arguments as well. Okay, so this, again, r squared, radius cubed over period squared, that's a constant. Okay, good. So you can always, this is the way to set these up, by the way. If you have any kind of problem along these lines, circular orbits, central force, you just go to the law and then just follow it where it takes you, or whatever you need to know about it. Good, so that brings us to the central force problem, the formal one that we're gonna study. Of course, Newton was there first. Because we now have to prove the rest of Kepler's laws. We have to prove that not only do we have circular orbits, but we have elliptical orbits, even those very wild ones that say the comets take. And yeah, so we'll build up the formalism for that. Just take that systematically. So the first thing you do, so next we're just gonna write central force and the two-body problem. It's also referred to as the Kepler problem. Central force. Central force. Okay. So here the idea is that we have this the other day. This kind of reminds us of our full coordinate discussion as well. So we have a force that only depends on the distance from the origin, and we have a unit vector pointing away. So if our origin is here, we've got distance r, and we've got a unit vector r hat vector over its magnitude. That's the picture there. But where's the second body? We actually have to do a two-body scenario and reduce it to this equation here. This will be the formal one that we study. So from two bodies to equation star right here. That's our task. And I will just sketch. This one's worth drawing reasonably generously. So we've got a mass, another mass. They both have their position vector. R2. And each one of these obeys Newton's law of motion, and what's acting on them is the force due to the other particle. Okay. So what we do to solve these is we define this relative vector r equals r1 minus r2. You notice it's pointing at 1 from 2 here. And we locate the center of mass. I always put a little star for the center of mass. So we got a little star right there. The center of mass. We have r. Center of mass is m1 r1 plus m2 r2 divided by m1 plus m2. Everybody familiar with that center of mass expression? Some of these moments highlight that. Okay. So what we're going to do next is now let the origin be at the center of mass. The new origin be at our center of mass. And what we'll do is, without relabeling, so that m1 r1 plus m2 r2 is equal to 0. With respect to the new center of mass, I just, if this is the origin, it's 0, then the numerator is 0. And then you can see what I'm doing. I'm taking, M1 times this plus M2 times that equals 0. So that's the idea. So now we have R equals R1 minus R2. So now we have these two equations, and we can solve for R1 and R2 in terms of lowercase, the unlabeled r. And let's see, we'll just plug one of these in, M1, R1 plus M2, and then the R2 will be R1 minus R. That'll be 0, then we'll have M1 plus M2 times R1 equals M2 times R. Is that right? Yeah. And that brings us to the first expression. So R1 is M2R M1 plus M2. And then R2 is going to be minus M1R over M1 plus M2. So now we have these expressions in terms of that relative vector, origin to the center of mass. Yeah, we're good here. So this vector R points from, in my picture, from the right to the left, right? And so the M2 is the one, the R2 is the one that gets the minus sign. Right? It's opposing the direction of R. So these are good. And now we're going to do Newton's law for both of these. So Newton's law of motion would be M1 R1 second derivative is equal to F, and M2 R2 second derivative is equal to minus F. You guys agree with that? So that's saying the force on M1 is equal to some force vector, and the force on M2 is equal and opposite by Newton's third law. So that's why I can identify these two, and equal in magnitude, opposite in direction. Now, if we go M1 R1 second derivative minus M2 R2 second derivative, we get F vector minus negative. Back up. That's not what we got to do. We have to do the following. We have to multiply the first equation. Here, I'll number this. You have to multiply the first equation by M2 and the second equation by M1, and then do that. So let's not skip any steps here. So we'll have M1 M2 R1 second derivative equals M2F and M1 M2 R2 double dot is equal to M1F. Negative M1F. And now I'm going to subtract those two equations, one from the other. So now M1 M2 R1 second derivative minus R2 second derivative M1 plus M2 times my force. And it's a race, but what's the difference of these two vectors, second derivative? Remember, I defined lowercase r as r1 minus r2. So what I've done is m1, m2, r second derivative equals m1 plus m2 times f. And if I write it this way, m1, m2 divided by m1 plus m2, put parentheses around this. And this is the force between those two objects. This is the one we can ponder for a moment. Because this double starred equation is what we had over here. So this combination of masses, it's a product divided by a sum. It has the dimensions of mass, right? Mass squared divided by mass. It's called the reduced mass. And we'll just call it M. M equals product divided by the sum. It's called the reduced mass. And we'll also say, and now F is a central force, and F being a central force is F of R. So that's the reduction of the two-body problem to a formal one-body problem, because there's just one vector here. And those equations I just erased will allow you to get back the R1 and R2 that we had before. Okay. So you get your reduced mass. Yeah, you know, let's quickly say something about the reduced mass. Which one in our picture was going to be much larger than the other? Okay, so there was our M1, this was our M2. Vector R was pointing from that one to the other. So let's let M1 be much less than M2. So we can think of this as much less, so much less than M2 that M2 is essentially stationary, right? And M1 is orbiting it. And if we look at M1, M2 divided by M1 plus M2, one's much less than the other, right? Then this one dominates. That's approximately M1, M2 over M2. So it's approximately equal to M1, slightly less, slightly reduced. Okay. Slightly less because I drew away the denominator. See? So if M2 is much, much larger than M1, this M2 dominates the denominator, and then M1, M2 cancel those, roughly M1. So that's a slight correction, so to speak, if you have a small planet orbiting a large body. But very crucial. So I've been told that you guys have heard of the Bohr model for the hydrogen atom. Niels Bohr, the hydrogen atom, one electron, one proton. So the proton's 1 or 10,000 times as massive as the electron. And what I heard was that when Bohr first did his model, he didn't use the reduced mass for the electron and the proton, so he was off by 1% or so. And he remembers his classical mechanics, plugs in the reduced mass, and just nails the hydrogen spectrum. These kind of stories your professors tell you, and then you tell the next generation, but no one went back to check. But it's a good point. So there's your reduced mass, pretty close to that. And now we can work our way into solving the central force problem, because we've reduced the two-body problem to a one-body problem. So I can erase, small erase everything. Start out with clean board here. Okay, let's see. So we can assemble all of our pieces now. So we're doing central force. We have a new understanding. We have this situation. Vector, that's the general central force problem. What about energy conservation? So next, let's mention conservation laws. And we have energy. But if we have the energy conserved, then we need a potential energy. And that has this general form. But we actually have to, let's go back a step. We actually have to prove this. So our potential energy is going to be minus F R over R dot dr along a contour from some point to some point, from point A to some point R. And in order for this to be a potential energy, this is going to have to be unique. So the value is going to have to be unique for arbitrary paths, for arbitrary contours. And that will be the case if a closed contour, if the integral over a closed contour vanishes. So this has to be unique. So we'll prove that later, right? That's a proof that we'll put, say, either on the homework or in a later discussion. So this defines energy and then and negative gradient u of r is equal to f of r. Right? Because then we'll have the same proof that we have for energy in one dimension. So conservation law, energy, so you have to be able to have a potential energy. And in fact, a central force, a true central force, always does have a potential energy function of that form. So then we have 1/2 m r dot squared plus u of r equals e equals constant. So to say that generally, you actually need some of the facts of vector analysis that we're about to talk, that we're talking about in math methods, right? So we're going to assume that and prove later. And the other conservation law is, so this was energy that we have to have. The other one is angular momentum. We're going to do these in the context of an in-body problem later on, but right now we can work with what we have here. So we'll have L is equal to R cross M B, right? force, define that as the angular momentum, and we'll take its time derivative, PLET, we'll have R dot cross R dot plus R cross R second derivative. That's an interesting one. This is just a scalar. We can pull it out. M R dot cross R dot plus M R cross R second derivative. What do you guys see for that first one there? Zero. What about the second one? Second one isn't trivially zero, but R cross, then we say, well, this is the central force problem. So R second derivative. Actually, why don't you pull that one out there? Shouldn't have pulled that one out. This would have been there. Let's go ahead and leave it. R cross and R second derivative. R cross, because now I can say I've got f of r, that's scalar, r over r. And we have the same argument we just had. We have a cross product vector with itself, pulling these scalars out, and so both of those are zero. They're parallel. And if the time derivative is zero, then L is equal to constant. So those are the two important conservation laws that we have always with the central force problem. Central force problem always has conserved angular momentum, and it always has conserved energy.
You say always going to be conserved?
With the central force.
But are there like any other forces that are still conserved?
Oh yeah. I mean, very simply, suppose you're in a circular orbit. You're orbiting something, forces towards the center, but you have a rocket on board, right? So you blast off in this direction, and immediately you have a non-central component to the force, and your angular momentum will also change, right? You can take yourself right out of that orbit. And the opposite example would be if you're in a circular pattern, but you have some kind of friction. Okay? You have some kind of friction, and that would cause you to spiral in, say. Okay? You have some kind of friction, you no longer have a conservation angular momentum. So this is the pure case. Even orbiting satellites, if they're close enough to the atmosphere, they encounter micro amounts of friction, but it adds up after a few thousand orbits, and the orbit decays. So that would be case of that. So good, we've got these two conservation laws. This one we're going to return to just for we'll return to this one right now. We have these two conservation laws. So for the central force here, we can actually extend this here, because this turns into f of r dr. I'm just going to write a to r. And that's actually pretty elementary. Okay? So the dot product between this increment of your contour with this radial vector is always just going to be the dr. So you can actually show that you're going, say, from this point A, we'll say as a vector, to this r out here. by some path. Any which way you go, then this dot product here, R hat, R over R, that dot product into there is just gonna be the radial increment outward. So that's why this dot product, just on geometrical terms, gives you the dr, the radial dr outwards. And because of that, you can easily do this kind of integral. So the example for this integral would be minus, I'll leave this actually, that'll be fine. So what was our Newton's law there a minute ago? We could have minus G M over R squared dr, and we'll get the negative G M over R if we let A go to infinity. Right, so that's the central force of the Newton potential, or the Newton potential, or the central potential of the Newton's force law. So we're going to have all those. So we're going to work on this in a little more detail, but I want to get to the punchline since we have both of our conservation laws. So yeah, we'll spend a little more time on these conservation laws and the conditions on these force laws. There's a little more to be said about that. But the one big conclusion with the conservation of angular momentum is that the motion is restricted to a plane. Okay. That's what we want to end the hour with. Conservation of angular momentum. So look at this. You've got L equals R cross, and R cross P, R cross M times V. And this is a constant. Okay. It's a constant vector. The left side is a constant. Now, you've got the cross product of two vectors. This one is always perpendicular to both of them, right? And that's why if, these two vectors always span a plane, right? And that plane is always perpendicular to the same vector. And so that tells us that because of that, motion is restricted to a plane. Motion restricted to a plane. And so guess what coordinates we're going to use for studying central forces? Yeah, plane polar coordinates. That's why, and they will be the simplest set of coordinates for this type of motion. And so that's what I can end the hour with. We're going to use plane polar coordinates, and we just started studying them. So that's all going to work out fine. Plane polar coordinates. Perfect. So yeah, we're going to leave it right there. And we have to talk about potential energies, but yeah, we'll do all this. Okay, yeah.
Did you actually assign any marks?
Didn't. We got a minute. Can I come up with another one? Actually, yeah. Yeah, just so, because, yeah, we want to have something to consult on. Here's what we'll do for the homework. We'll do these calculations. So that's actually kind of minor. Find U of R for F equals minus alpha over R squared. This is the one I just did. And for F equals minus KR, or R like that. So to put it in the same form. Yeah, it's not much.